You are about to listen to the full interview with Shubham Kanodia. Sections of it were originally included in our Fermi Paradox episode. Shubham Kanodia is the co-author of the research paper, How Much SETI Has Been Done? Finding Needles in the N-Dimensional Cosmic Haystack, an attempt to quantify how much searching for extraterrestrials we've completed. We dig deeper into Shubham's theory and why it may make sense that we have not found anything yet. We hope you enjoy.
So my name is Shubham Kanodia, and I am a graduate student in the Astronomy department at Pennsylvania State University. And I work on exoplanet research as well as SETI.
And how did you get interested in SETI research?
So I started working on SETI as part of this graduate course I took with Professor Jason Wright. And I was initially interested in learning more about the field because it's a topic that I guess fascinates pretty much everyone. But I wanted to see how I can contribute to the topic in a more quantitative manner.
Through that, you co-authored your paper, How Much SETI Has Been Done? Finding Needles in the N-Dimensional Cosmic Haystack. What specifically about that topic of trying to quantify how much search has been done drew you to it?
So that started off as a project of basically, as it says, how much searching has been done. And there were other aspects of SETI that I could have worked on because we had to do this class project. But this seemed the most exciting to me because this involves some heavy mathematical lifting, which was needed to come up with this framework, which you can use to take all the searches that have been done so far, put them in the system, and spit out numbers which tell you how effective or what fraction of the volume that we calculated do they cover. So we came up, so the framework itself is not something that is new in the sense the idea has been proposed. It was proposed in the 80s by Ray Tarara. But what we did is we provided a lot more rigorous framework where we took all the 9 dimensions and put them in one mathematical formula so that you can just take your search parameters, put them in that formula, and the formula will tell you that according to these assumptions that have been made for the framework and for this framework, which is valuing these parameters, this is how effective your search has been.
And how does that framework determine what parts of the galaxy are searchable from Earth? Like, what is it comparing your search parameters against?
So it has 9. So the typical cosmic haystack has 9 parameters. You have the 3 distance dimensions. You have the 3 distance dimensions. You have the frequency of the transmission. So what frequency? Is it in the radio? Is it in the optical? Is it in the infrared? And if in the radio, which is what we've limited this haystack to, which wave band? That's the 4th one. Then you have the transmission bandwidth. So how wide is the signal? Is it a really narrow band signal? What is the spectral width of the signal? So that's number 5. Number 6, I believe, is the repetition rate. How frequently does the signal get repeated? So that is basically to quantify that if I am staring at this patch of the sky every day for 1 hour, as an example, will I see the signal? So the signal is repeating once every year, and you're just going to look at it for 1 month. The odds are you're going to have a hard time trying to find it. So that's what the period dimension tries to capture. Then you have the polarization. So what's the polarization of the light? Is it circularly polarized? Is it linearly polarized? And so on. And I think the last dimension is the modulation. And that is something we did not cover. We mentioned it, but we did not cover it simply because it included many things that could not be captured in a very simple and succinct manner. And that involved a lot more calculations that we do not want to go into right now, because that also involves dealing with what kind of algorithms are used for the searches. And that is something we did not want to include in this framework. Oh, and I guess the last dimension, which is the most important, is the sensitivity. So basically, how sensitive is your receiver? So we took these 9 dimensions, 8 dimensions, and then put them together. And so to answer your question, for example, what part of the galaxy you are looking into, so we made this framework completely agnostic of which direction you're pointing your telescope at. There were some other frameworks that have been, some other versions of this framework that have been computed before, which do not look at just your solid angle or how much of the sky you're pointing at, but how many stars are you pointing at. So they try to quantify this dimension in the context of, if I'm looking at 10 stars in the galaxy, so that's 10 stars out of, let's say, 1 trillion stars. So that's your fraction, 10 out of 1 trillion. What we did is we did not look at the number of stars you're pointing at, but just what fraction of the sky. So that's how we're quantifying the spatial dimension. Just what fraction of the sky you're looking at. And that's the reason this is just one way this framework can be constructed. Now, if we could have taken another approach, and instead of looking at the solid angle or the fraction of the sky, we could have looked at the number of stars. And because of the decision we've made, the search, which is the most, which covers the largest volume in our framework, is the one which has a really large sky coverage fraction. So that's just a choice we had to make.
And you mentioned this cosmic haystack. Can we take a step back and explain what this metaphor of the cosmic haystack is, and what are these needles that you're looking for within it?
Right. So as I said, the cosmic haystack was originally proposed by Ray Tarara in sometime in the 80s, I believe, when it was constructed as this quote-unquote framework to quantify how much searching has already been done. So I believe this was during the time of Project Cyclops, when they wanted to say that, okay, the searching that has been done so far, how do we quantify that? And the reason you need something like this is, so you're starting off by looking in the radio and the radio region of the electromagnetic spectrum, but you do not know which part of the radio you need to look into. Should I look into the high frequency stuff and the low frequency stuff? Should I look between 1 to 2 gigahertz? The most frequently searched region of the frequency spectrum in the radio has been the 1.4 gigahertz because of the water hole. So people need to wanted to quantify that if I am conducting my search in a particular area, how much of the total fraction can I rule out? So that is one parameter that they wanted to rule out. Similarly, another parameter is how sensitive. So suppose you have a telescope that is 100 meters across, versus if you have a telescope that is 300 meters across, and they have sensitivities that scale accordingly. So how do you quantify the telescope times? If I'm searching for 1 hour with a telescope that is 100 meters in diameter, versus I'm searching at the same target for 1 hour with a telescope that is 300 meters in diameter, how do I compare how effective the searches have been? So the original framework was proposed to quantify these things and put them all in one cohesive manner, and they looked at the number of stars, the frequency in which they were looking at, and I believe also the bandwidth of the searches. So that is done to quantify the existing searches and how valuable would this future searches that they were proposing would be. So they wanted to say that, okay, we've done this so far, but what we are proposing to do will be so much better and build upon this. So that is how this started off. And then there have been various versions of this haystack through the years where people have added different parameters and they've adapted it to their searches and their studies to say that, okay, this is how our search or how our program compares to the previous explorations. So what we are trying to do is take all of these, learn from them, and put them into one cohesive structure. So that's what our framework, our haystack attempts to do. Put everything, combine all these parameters and put them in one framework. So the last thing is, so what are we searching for? What we are searching for when we construct this haystack is a radio signal. So there's no reason it needs to be just in the radio. It could be in the optical. And in fact, we are thinking about making a similar haystack for upcoming optical searches in SETI. And so we're searching for radio signals, so radio pulses that potential extraterrestrial intelligence civilizations would be sending at us. And what we're doing is we're searching for these radio, and most of the haystacks that are constructed, including ours, focuses on fairly narrow band transmissions. So the original thought was that they'll concentrate all of their energy in this really fine region of the electromagnetic spectrum and put a lot of energy in there so you can detect it across interstellar distances. So that's the kind of searches that have traditionally been looked at with these radio searches and that have been quantified using these haystacks, narrow band radio searches that are periodic, hopefully. It's pretty much agnostic as to the direction in which they're coming from.
I've heard that radio signals can degrade pretty quickly and that even our radio signals wouldn't reach very far into space. Is that a concern in the SETI search? Is there the thought that maybe, like, what are we looking for in a radio signal? And is there any possibility that they may not even be able to reach our planet in a way that we would be able to detect them from a civilization that maybe was at the same stage as us?
Oh, definitely. There have been tons of people who have thought about this and have put this into numbers. And the basic thought is that suppose I am sitting in New York and you're sending me a radio signal from San Francisco, you will need a much smaller, your power requirement will be much smaller for me to detect than if you were sitting in, say, China and you were using the same telescope, or the same transmitter. So if I was sitting in New York, I would need a much bigger telescope or a lot more sensitive telescope to receive a signal from China than from, say, San Francisco. So the principle is the same. If I was sending you a signal from Mars and now you're trying to detect it, it would be a lot easier. So that's what we're doing with the Mars rovers and the probes we have on Mars. But now if you have the same signal at the edge of the solar system, you will need a lot more power so that I can detect it with the same telescope. So there are two parts of the problem. One is the transmitter and the other one is the receiver. The bigger the transmitter, or the more powerful rather, the transmitter is, the easier it is going to be to detect it. On the other hand, if your receiver is bigger and more sensitive, so generally bigger helps because the larger the surface area of the telescope, it helps in it can make it more sensitive, more light gathering capacity. So therefore, a bigger telescope is generally better. So if you have a sensitive receiver, you can detect signals that are much fainter and potentially, therefore, that are coming from much further away. So that's what we try to quantify in the sensitivity dimension of a haystack. So what that says is that if you have a telescope of sensitivity, let's say X, you will be able to detect fainter signals from much closer away. But as you keep moving further away, you will need to shout a lot louder. So to put that in another way, if you're standing on Mars and you're trying to send me a signal using, say, a flashlight, and I have an optical telescope, I will need a much smaller optical telescope than if you were shining a flashlight from, say, Pluto. So it's the same signal, it's the same principle, but just in the radio. You need to shout a lot louder the further away you are.
And were you saying you're looking to adapt the framework to work for optical signals as well as radio?
We will be constructing a version of this haystack for the optical in the near future. Yes, that is the plan.
When searching for optical signals, what are we looking for that would identify something as potentially coming from an extraterrestrial race?
Right, so that is also an intense topic of research as to, say, when you detect a signal, be it in the optical or the radio, how do you classify it as artificial and not natural? Because the last thing any SETI researcher wants is to falsely flag a potential signal as artificial when it's just some weird natural phenomena. And we've seen that happen repeatedly. When we discovered pulsars, we jokingly called them little green men because it was such a strange phenomena which we hadn't seen in nature before. Likewise, now in the recent last 10 years, we've seen Boyajian stars, which in the Kepler data, which has this transit light curve that we'd never seen before, and people started attributing it to extraterrestrial intelligence and potential forms of super advanced civilizations that we do not know about. But now the most likely the scientific consensus is that it's most likely a swarm of dust or comets or something like that. So people are very worried as well as cautious about how do you flag these signals and how do you interpret them. So for the radio, one possibility is the bandwidth of the signal, how broad, spectrally broad the signal is. So by spectrally broad, I mean, just to give an optical analogy, if I'm shining a laser at you, the laser is quite monochromatic. It just has one wavelength. It has just one color. So I'm shining a red laser at you. You're not seeing the entire spectrum of light. You're just seeing a red color. Now, if I'm shining a flashlight at you, that's a white LED, which is emitting from red to the blue, and now you're seeing a polychromatic source. So it's the same analogy in the radio. Most searches have been searching for really narrowband signals, which are extremely difficult, or if I'm not mistaken, they are not produced naturally at all. So the bandwidth of the signal is one aspect in the radio. Another thing people think about in the radio, at least, is that maybe the signal will be repeated at specific periods, which are not likely to be natural. So, for example, if I was trying to get your attention, I would try to shine a flashlight, say for example, but not do it periodically, but modulate it with some weird frequency. So if I turn my flashlight on once every second, it's possible that it's just something far away in the background which you do not care about. But if I was modulating my flashlight such that now it's aperiodic or irregular, that it's on for 3 seconds and then off, or an even more extreme example would be if I turned it on and off in, say, prime number intervals, then it's a pretty much guaranteed sign that what is producing the signal is not natural, but artificial. So that's the period of the signal, the duration of the signal is one way. If that is modulated, that would be a very clear sign of something being artificial. In the optical, this problem is a little simpler in the sense that if you have, there's literally nothing in the optical astronomy universe that is extremely monochromatic and extremely powerful, aka lasers. So you do have lasers in planetary atmospheres that have recently been discovered, but nothing nothing at the same power levels that we're talking about when we consider optical SETI. So if there was a civilization that was trying to get your attention in the optical, and what we assume for civilization is that it will be next to a planet, it will be based on a planet next to a host star. So that means the host star is also growing in the optical, so it's really bright. Now you're trying to get my attention from a host star next to which is a planet, and you're based on that planet. But now you have to outshine the host star so that I'm not seeing the host star, but I'm seeing this weird signal that is coming from next to the host star, which I cannot resolve. And so you basically have to outshine the host star. So what we're saying is now you have to produce more energy than the star itself. For a civilization like ours, that is an impossible feat. Now, Kardashev proposed civilizations on his various scales, Kardashev type 1, type 2, type 3, and so on, where you have the energy not only of your host star, but of the local cluster of stars, and then you have the entire energy of galaxies and so on. But another way to do it is, instead of outshining the host star in the entire energy output of the star, you outshine the star in this really narrow wavelength band. So what that means is, suppose I was standing next to the sun, I'm on planet Earth and I'm trying to get the attention of someone far, far away in a neighboring star system. Instead of trying to outshine the sun in the white flashlight region, I'm going to shine this really powerful laser that outshines the sun only in this narrow wavelength region of, say, red. So I pick a laser color and I'm going to make it really, really spectrally pure. So there is no energy that I'm transmitting anywhere else but for this really narrow red region. So if I wanted to outshine my star just in this really narrow region of light, then I would require lesser energy, because instead of spreading my energy over, say, the entire optical spectrum from the blue to the red, from the radio to the X-ray, I'm going to concentrate it and shine it just in this really narrow red or blue or green region of the spectrum. So that is one method that has been proposed that people are going to be looking for, to search for these really narrow frequency or narrow wavelength laser pulses.
So it sounds like these optical signals that we're looking for wouldn't necessarily be something that we're accidentally picking up from another civilization. These would have to be intentional signals that the civilization was sending out in hopes for somebody else to recognize it.
Well, that's not entirely true. So of late, we have started using laser transmissions to communicate with our satellites around in orbit around the Earth, right? And we use a laser of a particular frequency, of a particular bandwidth, and of a certain power level. Now, it's possible that you will intercept certain lasers from extraterrestrial intelligence or extraterrestrial civilizations that are accidental, that they weren't intending to transmit to you, but they were using for communication, and that you just happened to intercept. So one problem with these searches is that there's literally so much that we do not know. So we have to make certain assumptions and build upon them. And that is one thing. And the only priors we have, the only other civilization that we know of is our own. So we try to assume, or we try to base off on how technology has developed for us. And if it was developing in the same manner for another civilization, what would be the potential signatures of that? So it is possible that we do detect these accidental transmission signals, say in the radio or in the laser, but the odds of that happening are quite low.
You mentioned in your paper there's either a quote or you write yourself about how the search so far has been likened to a cup of water out of the ocean and seeing if we could find a fish in it. Could you maybe, and I probably misstated that a little bit, but could you maybe talk to that idea of like how our search thus far is pretty microscopic in terms of everything that's out there?
So let me give another analogy for this. So you are based in San Francisco?
Yes, that's right.
Okay. So suppose I tell you tonight that there is this really cool event happening in San Francisco. And that if you find that, that will be the best thing in your life, and that's going to be this really life-changing thing. But I don't tell you where in San Francisco it's happening. I do not tell you what time it's happening. I don't tell you if it's tonight, if it's next month, if it's next year. I can't even tell you if it's already happened. But there is this event that might happen there that if you were to find, it would be amazing. I do not tell you what it is. I don't tell you if it's a book reading or if it's a dance competition or if it's a band playing, your favorite band playing. So I'm giving you absolutely no information. But now I'm going to tell you that if you find it, it'll be amazing and really cool. So now you have to think about, okay, if I want to find this thing, how can I go about narrowing it down? So you would probably play the odds and say, okay, maybe it's not going to be in the middle of the busiest intersection in San Francisco. It's probably not going to be at noon. So, okay, I will go to, I don't know, a music concert venue and see if there's something there at 7 in the evening on a Saturday. Because the odds are, if it's music related, it's going to be over here. If it's not there, maybe I'll try a library or a bookstore and see if it's a book reading or something. So you'll systematically start narrowing down and eliminating your possibilities. Now what happens, suppose after 2 days of searching, you say that I have looked into these places and I have ruled these out. So that is what we're trying to do. In the last 40 years or so that we have been looking, we have tried to quantify that out of the total possibilities, how many have we ruled out? And the reason the total number of possibilities exist are so broad and so unconstrained is because we didn't want to make any assumptions and narrow them down. And we wanted to be as agnostic and as wholesome as possible, in the sense that we do not want to assume that, oh, they will be transmitting from stars, not from empty space. They will be transmitting only in this region of the wavelength band. Or they'll be transmitting only from 1 second to 1 hour, not anything beyond 1 hour. So we did not want to make any such assumptions. So in the most conservative scheme possible, we say that this is the total amount you need to search. So now suppose I told you San Francisco, if I didn't even tell you that, if I said there's something really cool happening on Earth, now how long will it take for you to search for that? I do not tell you the time, I do not tell you the place, what it is, etc. So that's what I believe it's one tub of water, one bathtub of water in the entire ocean. So the implicit message behind that is, before we say, okay, we've been looking for the last 40 years, because that's what many detractors say, that we've been looking for the last 40 years and we haven't found anything. But the truth is, the amount we've actually looked in this gigantic framework is so small, we can't really say we've ruled anything out. We can't say we've placed any upper limits on the broader picture. There have been searches which have looked at the star, and okay, you can say that this star or this stellar system, we do not see anything that is being transmitted in this wavelength region at this time for the 5 minutes that we looked. That's the only constraint you can place. But you cannot say anything about that. There doesn't exist a civilization on that star, let alone in the entire galaxy, or the fraction of the galaxy that you've looked at. Because the fraction we've looked at is so damn small.
Do you worry that there's maybe any negative repercussions to framing the search as vast and as hard to identify any signals as like this? Like, do you think that's a turnoff to any researchers to even enter the field because it is just so daunting?
Well, so the number that we placed is more of a qualitative estimate to show that how little we've looked. And the quantitative aspect of the framework is to compare different searches, that, okay, this search is done this, while the other one, which had a different goal in mind, this is how it stacks up. That's how you can compare it. But the number itself is not to say that, okay, if we have put in this much effort in the last 10 years, we need to scale it up by a factor of 10 billion to find something. That's not what the message behind the number is, that you need to put in 10 to the power 18 more units of effort to find something. It's just to show that this Fermi Paradox that we're talking about, that we've looked and looked and looked for the last 40, 50 years and we haven't found anything, is not really true, because we haven't really looked that much. And before we make any statements, any such bold statements, that we've been looking and we haven't found anything, we should take a step back and think about how much have we actually been searching and how much effort has been really put into it and how much more should be put into it.
Yeah, you mentioned the Fermi's Paradox. That's actually the topic of our episode. Could you explain in your own words your understanding of what Fermi's Paradox is?
So I think the best way to capture the Fermi Paradox is this XKCD comic that I can send you. And let me just pull it up.
Okay. Yep, I have it open.
So as you can see, I think that one frame basically captures the essence of the Fermi Paradox.
And could you maybe, just because this is going to be audio only, and I can definitely link to this in our show notes, but could you maybe just kind of describe what is happening in this image and kind of like what the idea behind it is?
Oh, sure. The basic essence of the Fermi Paradox is that we have been looking for so long and we haven't found anything. And if we say that life should be everywhere and that the mechanism of formation of life should be fairly ubiquitous, then considering the number of stars in the galaxy, even if the odds are small, the universe should be teeming with life. And then the second point is, considering the age of the galaxy, life that has evolved, even say a tiny fraction of that age before us, and a tiny fraction of billions of years is millions of years or even thousands of years before us, they would have evolved to a stage that they would now be colonizing different stars and different stellar systems and traveling across the galaxy. And if that is so, the whole galaxy that we observe should be teeming with life. And since we do not see that, our life probably doesn't exist. Extraterrestrial life doesn't exist.
Could you maybe talk about some of the current technological and also societal limitations for our civilization to be able to search for extraterrestrial civilizations? What are some of the obstacles we currently face?
I think some of the obstacles we face are technology, in terms of we still use rocket fuel for traveling across the solar system. Something like that is not a feasible option when you want to travel interstellar distances. There have been recent projects and studies into looking into what if you can use photon energy itself or light from the sun to propel you as a light sail. Then there have been searches or there have been projects which are looking into using nuclear-propelled rocket engines and different technologies like that, which would make it a lot more, I wouldn't say easier, but technically feasible to move across interstellar distances. The main challenge is the technology, and that is because of the distances involved. We're talking about the closest star is 4 light years away. And each light year is about 1 followed by 16 meters. We're talking about numbers which are extremely hard to fathom. And because of the distances involved, I don't think we've still reached the point that we can say send a human across interstellar distances. We're not sure that we can send a human to Mars, which is right next door compared to the stars that we're talking about. We just don't have the technology in the sense, in the context of propulsion, in the context of healthcare, or the political, the backing to spend that kind of money to develop that technology, because right now, I guess the powers that be do not see the advantage in that.
Do you have any future projects planned in the SETI space?
So as I said, one thing that we're thinking about is the optical haystack, which is similar to what we've done, but in the optical region of the electromagnetic spectrum. And another thing that we're thinking of is at Penn State, as part of my graduate work, I'm also working on building these 2 spectrographs called the Habitable Zone Planet Finder, and the second one is NUID. And these are radial velocity spectrographs which will search for Earth-like planets, or planets which have the potential to have liquid water. So they're in their Goldilocks zone of their stars. And the spectrographs will do this using the technique called radial velocity, which basically takes the light from the star and splits it into thousands and thousands of colors, and then sees how those colors move around. Now, a byproduct of doing this is you have what is called a really high resolution spectrum of the star. So you're taking the light from the star and, as I said, splitting into it thousands of colors. What you can do is, once you have this, you have a really nice map of the star. And if suddenly in this map you see one of the colors, one of the lines, become really bright, which is exactly what I was talking about earlier when I was referring to the optical signals that could potentially be sent. So you could outshine your star, not as a whole, but in a narrow wavelength region. So we're planning to use these spectrographs with the data that is already there. So we don't need to conduct more searches and spend more money to build new instruments. We just need to look at existing data and comb through it to see if we see any such peaks jumping out.
Do you think that there's been any, I know there's been a few signals that have been detected that have caused excitement that have been disproven, usually in the end. Are there any signals that have been detected thus far that still remain mysterious and possibly could be extraterrestrial in origin?
So I think the only signal that I know of that had been detected and is still mysterious is the WOW signal that was detected in, I think in the 1970s by the radio telescope called the Big Ear, which was, I think, built by Ohio State or managed by Ohio State. And it was this really powerful signal. It was, I think, 20 sigma, so many, many thousands of times more powerful than their background, stronger than the background. And they detected it for a few moments, and then it was never seen again. And I think there have been many hours of radio telescopes looking at that patch of the sky, but they haven't found anything. So that is the only signal that I can talk about.
Hmm. And that was a radio burst?
That was a radio signal, yes. I wouldn't call it a radio burst because we've recently discovered a radio phenomena called fast radio bursts, which is an astronomical phenomena associated with certain events. So I wouldn't necessarily conflate the two because there hasn't been any study that I know of that associates the vast signal with a radio burst.
If any of our listeners were interested in helping to get involved in the search for extraterrestrial life, are there any contributions that people can make to help further this research?
Yeah, so as I was saying, there have been searches done over the last 40 years. There has been great work done by the SETI Institute and recently the Breakthrough Initiative. And what the SETI Institute has is this thing called SETI at home. So one issue with these searches is they're getting so much data, the amount of computing power needed to analyze it is simply quite limiting and quite a restricting factor. So what the SETI Institute has done is they have kind of crowdsourced data analysis. So what you can do is you can download this software called SETI at home on your computer, on your personal computer. And then whenever your computer goes to sleep or goes on to screensaver mode, instead of the computing resources lying vacant, what it will do is it will download some data from the internet, from radio searches for such signals, and silently run it on your computer and analyze it. And then when your computer turns back on, it can show you what searching it has done and the amount of data it has looked at. And then it will send it back to the servers and add it to the giant collection of data that they've already gone through to make certain predictions or analysis to say that, okay, this is the searching we've done and this part of the sky we've looked at, now let's look at this part of the sky and so on. So SETI at home is one of the best ways that I know that can be helped with. And anyone can do it. You and I we can just download the software on a computer. It's available on the internet, SETI at home. And it just works in the background. You don't need to do anything and it works pretty well.
That's awesome. Do you have any last thoughts or comments that we haven't touched on?
I think I can just end by saying that there are many people who have been working on this and who've devoted a big fraction of their life on this search for extraterrestrial intelligence. And I think the prime example is Ray Tarara, who's been basically trailblazing and who's pioneered so many of the things that we are now working on. And people often say that, okay, as I said, we've been looking for so long, these people have done so much work, why haven't we still found anything? And I think what we need to understand is the amount of work that is needed and the number of people who are working do not match. These people have put in so much time, but we need a lot more effort and funding to make an appreciable dent in this field. And the best part is that these searches are not in a different field from astronomy. We are looking at the same sky. We are looking using similar instruments. So one amazing thing that is happening now in astronomy is we are building these gigantic telescopes and conducting these surveys of the entire sky. You have, in the optical, you have the large, the LSST, the large coming up in Chile, which is an NSF-funded project that is going to get terabytes of data every night. In the radio, you have the square kilometer array coming up in the southern hemisphere, which is going to be this gigantic radio telescope that will generate like petabytes of data. So what SETI needs as a field now is not money to build its own telescopes, but there are already so many existing wonderful telescopes that are existing or are coming up in the next few years that it needs the people power and the computing power to go through this existing data and crunch it and make some analysis and crunch the numbers to make some conclusions as to what fraction of the sky that we have now ruled out. And I'm talking about these gigantic searches because they're going to look at the entire sky day in and day out. And those are the kind of searches that will make a big dent in these numbers which look so daunting right now. A telescope like LSST or the Square Kilometer Array in the Southern Hemisphere, they will make mincemeat out of many of these numbers.
Let us know why you think we haven't found evidence of alien life on our Twitter and Instagram at strange_phenom and on Facebook at Strange Phenomenon, all one word. Please give us a review and subscribe on your favorite podcasting app. Visit www.strange-phenomenon.com for a full list of sources and more episodes. Strange Phenomenon is hosted by Ray Tarara. It's written and produced by RJ Blake and Ray Tarara. Theme music by Tara Monk.